which is the mole on page 20. It starts on page 20. And hopefully you remember from phys sci that 1 mole of anything has 6.022 times 10 to the 23 particles. You might notice on your formula sheets that Avogadro's number is now 4 sig figs, 6.022.
Is that a chemistry thing, or is that changed on the phys sci sheet as well?
No, it's just chemistry.
Oh, it's just
This allows you to calculate to 4 sig figs if needed. You've got that in there. Whereas you would be limited to 3 sig figs with the other one. So the mole is like the word dozen. It's a shorthand way of representing this many pieces. It could be grains of rice, it can be chairs, it can be more likely to be atoms or molecules. And if you look on your formula sheets, it's on the second page. It's the top. Oh, it's on the top part there of the formulas. So page 2 has a page of formulas, and we've got these relationships here, where little n is the number of moles, n with subscript a is Avogadro's constant, or Avogadro's number, and n, the capital N, is the number of particles, whatever's relevant to the question. And so we've got our 2 arrangements there that are commonly used. We're either finding the number of particles or finding the number of moles, because Avogadro's number is a constant that we're just going to use. We wouldn't be finding that in the context of our questions. And we use this in conjunction with this is probably one of the most important relationships to understand. And this is where we look at the relationship between mass and moles. So again, the n is the number of moles. Little m here is the sample mass. And the big M, capital M, is the molar mass of whatever that happens to be. So atomic mass could go in there, or the formula mass, or the molecular mass, all of them go in there for the mass of 1 mole of that substance. And we can link the 2 concepts together through n, because n is present in all those places there. The other arrangements of this, m then capital M equals the sample mass divided by the moles, and little m is equal to the number of moles times the molar mass. So that's just rearranging that formula there. Okay, so if we look at example on page 21, the first example, it says we've got 3.4 times 10 to the 24 molecules of sulfur trioxide. Determine the number of moles and then the number of mole of oxygen atoms. So we know we're finding moles. So we know then, we want to know that, and molecules are particles, aren't they? So what we know then is the number of particles. So if we want to find n, we have that, we can also then use Avogadro's constant to find n. N equals n on Na I highly recommend you use the fraction button on your calculators when you've got powers, or you'll end up with a crazy answer. Alright, unless you've got your brackets under control. And then, because this was only given to 2 sig figs, our answer can only be to 2 sig figs as well, which is where we get our 5.6 mole. The second part of the question, we wanted to find the oxygen, and it's just oxygen atoms, not oxygen the gas, so it's just O. For every mole of sulfur trioxide, we have 3 moles of oxygen. So we just need to multiply this answer here by 3, which then gives me 17 moles of oxygen. Atoms. Any questions about that? Okay, so if you look then, if you turn the page to page 22, if you look at example 2, determine the mass of 54.7 grams of silver nitrate crystals. Well, I'm not going to go through this, how we work out the molar mass of the silver nitrate, because we've just done that. We're just going to assume that the calculation in the book's correct, 169.9 grams per mole. And we're asked to determine the mass, which is the lowercase m. We've got big M, and so, we're not determining the mass because we've given the mass. What we're actually determining is the number of moles. Yes, because the mass is 54.7. So again, it's not set out like this in the book, but I would, this is a better way of doing it. Now I'm calculating the moles of silver nitrate. So I've got the capital M in brackets telling me that that's the mole. This is my calculation of the value for the molar mass of silver nitrate. This is my justification for my calculation. This is the formula I'm using. Now I'm substituting into that formula, but I'm saying what I'm substituting in. So I'm substituting in my silver nitrate. So that was example 2. Example 3, what is the mass of 4.97 mole of solid carbon dioxide or dry ice? So again, we're finding the mass. I'm not going to calculate the molar mass of the carbon dioxide, I'm just going to use it. So that was given, and so this time we've got we've been given also the moles, 0.97. So M equals M times M. The mass of carbon dioxide is equal to the moles times the mass. So our answer has to be to 3 sig figs because the 2 parts of our question will give them to 3 sig figs. And then for question 4, we're back to particles. We're asked to find the mass of 1 molecule of nitrogen dioxide. So the molar mass of nitrogen dioxide, just going to use, we want, we know that Avogadro constant is 6.022 times 10 to the 3. And we know that our formulas, our particles, so n equals n times NA, and we also know that n equals little n and big M. And we can combine them together. So n would equal n on n. Does that make sense? Just swapping that around. So that the mass of one molecule then is what we want to find. So we're going to have, when we're thinking about our particles, there's only going to be one, isn't it? One particle. If I'm finding m, it's going to be m times n divided by Avogadro's number, where n is 1. So anytime it's talking about atoms, molecules, particles, etc., we need to be looking at the Avogadro's number formula. But for other masses and moles, we're going to use the other relationship. All right. Any questions? No? Do you remember doing that last year?